So recently I watched this video from Blackburn Defense, and it was very interesting looking at a statistical analysis of shot dispersion, and they even built a website with a dispersion visualizer on it. And the guy had a couple of main points from the video, and for the most part, I thought he did a really good job of, making the points that, five-shot groups are a little too small to really draw meaningful statistical conclusions from. But he also said some things that I think might mislead people about what to expect whenever you see a large group target, meaning if you shoot more than 5 shots, what should your target kind of look like? And what I've got up on the screen right now, this dispersion visualizer, is one of the sources of what I think could be some poor conclusions. Specifically, if we look at this little plot here, which is kind of a density function for the dispersion. And I think this stems from mixing some language with statistics. And it's somewhat of a semantics argument, but whenever, he says that groups are not normally distributed, you kind of got to be a little bit more specific. What do you mean by a group? And specifically, these distributions here are not the group distributions. This is the distribution of shot dispersion. Now, it's also mirrored, which is kind of weird once you really understand what this is plotting, because there shouldn't be two humps here. The way he is plotting this distribution, there should really only be one of these. It shouldn't be mirrored because, I don't know, maybe he was trying to point out that this would be symmetric around the target, but again, this starts to give some poor implications about what your target should actually look like. And so to really dive into this a little bit more, I built my own simulation in Excel to do very similar things to what he's doing. Now, I do simulate my shots a little differently than he does, and I will talk about that later in the video because the way he does his dispersion simulation is part of the source of what I think could be some real confusion, because believe it or not, the way you simulate shots can have a real implication for the distributions that you see on target. And I'm not going to argue that the way I'm doing it is the best way. It is, though, more of a traditional ballistics approach to what shot distributions will look like on target. Now, I've got a bunch of stuff here on the screen, so let's dive into it. So right here in the middle, I've got this big plot, and this is a simulation of 100,000 shots on target. And the way I did this simulation is by picking random XY coordinates, where both the X and the Y coordinates are independently normally distributed random variables. And so I've got little distribution functions over here on the right for both the X coordinates and the Y coordinates. You can see both the X and Y coordinates look like bell curves, and I did use random normal distributions to build these. I've actually got on a different tab over here on the RNG tab, you can see the little functions that I used where I specified that both the X and Y would have means of 0 and standard distributions of 0.3 inches. And so then I just pulled a bunch of random numbers using Excel's built-in functions. And then I just plotted these because once you've got X, Y coordinates, you can just plot all these. Now, if you notice, it's just a big wall of dots, so that's maybe not as helpful if what we want to know is dispersion. So how do you measure dispersion? And well, it kind of depends on what you mean by dispersion. So what I did to measure the deviations, which is going to be the absolute distance away from the intended point of impact. Now, whenever you do this, you have to understand that essentially what you're doing is solving for the hypotenuse of a triangle. And as we all know from the Pythagorean theorem, a squared plus b squared equals c squared. So if I have X and Y coordinates, the distance of that point from the intended target will simply be the square root of a squared plus b squared. And you can see here in the deviations column, that's what I've got. The square root of x squared plus y squared equals the distance from center, or the deviation. Now, one thing that is absolutely correct is the distribution of deviations is not normally distributed on this target. Even though both the X and the Y are normally distributed, the hypotenuse of the triangle formed in this situation is not normally distributed. It is actually a chi distribution, as Blackburn Defense mentioned in that video. Specifically, It is a type of distribution known as a Rayleigh distribution, and this is used in ballistics for the calculation of things like circular error probable. Even on the Wikipedia page, as you scroll down, you see under applications that in the field of ballistics, the Rayleigh distribution is used for the calculation of circular error probable, because the Rayleigh distribution is a very specific chi distribution when both the x and y coordinates are normally distributed and independent with the same mean, which is what I did in my simulation. Now, all that's fine, but the real question is, when you say groups are not normally distributed, there is a problem in looking at this distribution and calling this groups. Because what this is a distribution of distances away from center, but it's not the same thing as what this picture actually shows. This picture actually shows a bivariate normal distribution. It is normally distributed in 2 dimensions. And just to drive that point home, if I do a 2-dimensional version of these histograms, right? So both these charts are histograms to show you the shape of the distribution of the x and y variables. And again, I'm basically using this for horizontal and vertical dispersion, right? These are both bell curves. And if you do a 3-dimensional combination, you get a 3D bell shape. And to drive that home, I've actually got another tab where I did a 3D histogram. And so I've got this 2-dimensional grid, and in each one of these is a count for how many observations fall in these bins. And if you plot this thing, you get a 3D histogram which shows the impact density on target of this simulation. And sure enough, it looks like a bivariate normal distribution. It does not look like a donut, which is what you would get if you think that what you're going to get is some sort of rotated version of this chi distribution. That's not what happens on target. And again, I'm just trying to drive the point home that I don't want people to be confused by what they think they should see, because one thing that he does in his video is he goes and he shoots a bunch of groups and he says, look how few of them landed at the center.
The distribution that we predicted based on the previous software. And you can see the real life data matches our prediction. It is not normally distributed. The dead center is the least likely place for a bullet to go, and somewhere around this first circle here is the most likely place.
But there's a problem with that type of logic, because the center of a target is an infinitesimally small point, and probability doesn't work at individual points. There's a reason why we have to do histograms. You have to put things into ranges, and it turns out that the center is the highest probability density range, even though on average shots don't land at the center. And that seems like a very paradoxical, conflicting statement. So let me try to make more sense of this to show, like, what should you actually see on a target, and why is it that the dispersion isn't around 0? It looks like it is, like nothing should land at the center if you look at this picture, but on these pictures it looks like the center should be the most likely. And the answer is, well, actually both are true at the same time. So what happens on this chart whenever you take random draws from both the x and the y variable? Well, to land at the very, very center, you have to draw from the very middle band on x and the very middle band on y. You cannot pick any other band from either the x or y. There's only one combination of values that can land at the middle. And if you take that to the limit, there's a 0 probability that that ever happens, because you would have to pick exactly the same 0 value from both distributions, and that's very, very unlikely. However, as you get further away from center, you actually arrive at a situation where more combinations of x and y variables can get you to the value that you're looking at, which is weird. But there's a different way to think about how probability ends up in this picture looking different than this chart of the histogram of the deviations. Again, how can we reconcile that the deviations have this weird chi distribution where the x and y variables are telling us that the center is the most probable outcome? Well, It's because the center has a very small area compared to the rings around the center. And when you're doing probability, you don't do probability at a given point, you do probability within an area. And so I've got some extra stats down here pulled from these numbers. So these statistics are based on a bullet diameter of 0.264, 6.5 millimeters, 6.5 Creedmoor, that's what a lot of people shoot. Well, if you assume that your bullet has a diameter of 0.64, one thing you might ask yourself is, what's the probability that I get a bullseye? Well, the rifle that I've simulated in this target is a fairly accurate rifle. The average 3-shot group out of my 100,000 shot simulation is 0.76 inches. The average 5-shot group is right at 1 inch, and that's basically what I used to pick the numbers. I wanted a rifle that would, on average, group about 1 inch for 5 shots, or what most people would call a 1 MOA rifle. So this plot is a 1 MOA rifle shooting at a target 100,000 times. If you've got a 1 MOA rifle, and again, I'm speaking loosely here, there's about a 9% chance that you'll get a bullseye out of a shot, meaning 1 out of every 10 shots should make contact with the center of the target. Now, how do I know that? Well, what I did, if you look up here at the formula, I counted all of the impacts where the deviation is within 1 bullet radius of the center of the target, because in the real world, we aren't shooting dots. We are shooting physical objects with real physical diameters and properties. And it turns out that if you shoot at a real target with a bullet with a diameter of 0.264, if that bullet lands within 0.132 inches, it will strike the center of the target. And so there's about a 9.14% chance that with the distributions that I used, a bullet would strike the center of the target. So to illustrate what these numbers are trying to tell us, again, the probability of hitting a bullseye with this rifle shooting a bullet with a diameter of 0.264 is the probability that a bullet lands within half the bullet diameter of the center. And so I've made up this little kind of chart in Inkscape just to kind of show you what I mean. The probability of landing, off of the bullseye just a little, but basically within a full bullet diameter, so that you don't strike the bullseye, but you're not that far off, is about 22.84. Going to 2 bullet diameters away from the middle, that area captures 46.66. Now, these are non-cumulative, so these probabilities are basically the probability of landing in a different colored ring on this picture. So the very center has a probability of 0.914. The orange ring around it is 22.84. The yellow ring catches 46.66% of shots. And this is kind of what that chi-square distribution is trying to tell us. Now, it may seem like in the middle, you wouldn't see very many because only 9.14% of bullets land in an area that would be touching the very center of the target. But that's misleading, because what you don't maybe notice right away is that these different rings do not have the same area. The center dot is smaller in area than the orange ring around it. And that's smaller still than the yellow ring. And as you go to these larger outside rings, they get bigger and bigger in area. So there's more room for a bullet to land. So whenever you're talking about probability density, the center is actually the highest probability density area. It's just that it also represents the smallest area of the target. And so I actually plotted that too. What is the area of 1 bullet, basically? If you've got a bullet with a diameter of 0.264, that's an area of 0.05 inches that bullet has to strike to be a bullseye. That has a probability of density of 1.67, which if I turn these into percentages, you'll realize that is exceptionally high. 167% per inch. That is the probability density at this point. Now, as you move farther away, what happens? Well, the probability density falls off, even though the likelihood of landing in that area is actually the highest in that third ring. basically in this yellow portion. That is the highest probability area, but the problem is it's a larger area than either the red or the orange areas of this picture. And so both things are true. The highest probability density area is the center of the target. That does not mean that it's the area that's most likely to catch a bullet because, well, whenever you're measuring things in dispersion, the distances further away from the target represent larger areas of the target because that's the way area works. As you go further out on the target, i.e. as you increase the dispersion, the area that dispersion represents grows because dispersion is just a univariate distance. It does not capture the area. Whereas when you're looking at this target, the center is smaller than the areas around it because that's the way 2D graphics work. And so I just didn't want people to get confused in thinking that they should expect to see some sort of donut shape because, well, dispersion isn't normally distributed. Whenever you say groups aren't normally distributed, that's kind of a misleading statement because the position of those groups, yes, those are normally distributed. The deviations are not, but deviations aren't directional. And so whenever you look at these deviations, it can be a little misleading. What should you see in a group? Again, statistics is a little complicated and it's not straightforward sometimes how to think about these things. The deviations, no, they are not normally distributed, but your groups kind of are if what you mean is what should your groups look like on the target. Groups should be centered bulk dots. You should see probability densities, impact densities like this bell curve. Most of your shots should hit the middle, and as you go further away, you should see the dispersion kind of thin out. Now, in their empirical tests, they claim, back them up that, you know, the dispersion matches this chi distribution, and it does, but their target doesn't look like there's nothing in the middle. That's misleading. Again, dispersion and what you see on target are measuring two different things. These deviations do not have directionality. So again, it's kind of a weird thing to harp on, but the way the information was presented, I thought could mislead some people that they should expect not to ever hit bullseyes, that they should expect their bullets not to land toward the middle of their target. And that's not true. Your bullet should hit the middle of your target. The problem is the way we define the middle often makes the deviations look like nothing's going to land in the center. And the reason for that really is, well, the center is actually quite small on a target relative to these rings as you measure longer distances away from center. And a quick thing to point out is as you double the distance from center, the additional area is 3 times larger. And so, I mean, this is a very straightforward thing that, you know, pi, you know, whenever you look at these formulas, it's basically some version of pi times radius squared. So if you double the radius, the area is multiplied by 4. Well, 3 parts of that is new area to 1 part old area. And so again, as you double the deviation, you are increasing the area that a bullet can falls into, because again, that's how circles work. So whenever you see this deviation plot and it's like, okay, things are not normal, this is a chi distribution, nothing really lands exactly at a 0 deviation, that's not the same thing as saying bullets shouldn't land in the middle of the target. The way this thing is measured is just a unidimensional linear measurement. But when you map that into a 2-dimensional circle, going from 0 to 1 is an infinite increase in area. Going from a radius of 1 to a radius of 2 is an additional 4 times as much area for that observation to land in. And so, you know, whenever you see this density function here for the deviations, it's just not trying to communicate the same information that the plot of the shot chart is trying to tell you. So this leads me to the way they did their simulation and one of the weird things that comes out of that. Now, one thing that's great is that Blackburn Defense actually posted the visualizer that they did for their dispersion analysis. And so we can hit this 100,000 sample and see this little plot and, the same charts and stuff that they were using. And this kind of led me to look at the way he's doing his simulation and point out one thing that is a little odd. So every time you hit this draw, you can see these two lines. He's doing two random vectors, but to do a vector, you actually need two random variables to generate a vector. And so one thing that I would point out is in these, like if you just pick one variable and say draw, you've got like these multiple random variables, and the way they interact is a little odd whenever you're doing random vectors. So this is kind of off in the weeds, and so this is not a huge criticism. It's just an oddity of the specific way that he is doing this simulation compared to what I'm doing. So in my simulation, the underlying variables are x and y coordinates, and both are generated independently with normal distributions. What he's doing seems to be generating a random direction, and here I've got a column with radians, and that's going to be a random angle. And then he's generating a random magnitude. Now, what's odd with this is to generate a random angle, you can't use a normal distribution because that doesn't really make sense. You kind of need to use a uniform distribution, and the magnitude can be a random normal distribution, but in order to do that, you need both a mean and a standard deviation. Now, on his visualizer, he only allows for a standard deviation and not a mean, and so I really don't know exactly what he's doing. However, presuming that he's using a uniform distribution for the angles, which is basically saying any direction is equally plausible, which seems to make the most sense, you actually come out with some weird stuff. And that is because whenever you're using angles and magnitudes to do a vector, that actually is two things at once, and you can extract x and y coordinates from the angle and the distance given in these two things. And it looks like he's actually doing two separate vectors and then adding them together in this simulation. And I say that because you can kind of see, let me zoom way in on this. You'll see there's two lines, and I believe every time you click a point, he's doing like two random vectors added together, which actually means he actually has to predict four random variables and then put those all together. But the problem is whenever you combine the uniform distribution of the angle and the random normal of the distance, you do not get normally distributed x and y coordinates out of those combinations. And so let me show you one other oddity to this specific simulation method. So like I said, I have gone ahead and put up this data in the RNG tab. So I've got a random function that predicts a random angle using a uniform distribution. So to predict radians, I've got random number, and that's going to be a random number between 0 and 1 times 2 times pi, and so that will generate a random number between 0 and 2 pi, which is a circle in radians. And so this is just a random angle. I have done that twice because, again, he seems to be doing two different vectors. And so for each vector, I also have a randomly normally distributed distance. And so this is using a normal distribution. I'm generating a distribution with a mean of 1 and a standard deviation of 1, which I think is what he's using. I'm not exactly sure, but it doesn't matter for what I'm going to be showing you. So I've got two vectors, and now I need to add them together and extract the x and y coordinates, which is possible because these basically form a hypotenuse, and then you can pull out the x and y. Here, I've got that. I'm using cosine functions. This is basically how you pull x coordinates out of a vector. Since you've got two vectors, it's actually as easy as adding the two x coordinates together for the outcome. And then the same thing for the y, except for you use a sine function, and you can extract the y coordinates from these two vectors. And so I've got the x and y coordinates from all of these combinations of two random vectors. So let me drop them into my sheet, and I'll show you some weird things. So over here in my data, I actually have everything built with formulas. And so if I come over here and I just drop these into the x and y, watch how the distributions change for the x and y coordinates. Okay, there you go. Do you see how peaked these are? These are no longer normally distributed variables. I'm not sure what distribution the x and y coordinates have. It's obviously some sort of a symmetric distribution, but it almost looks like some kind of Laplace distribution or something weird because it's very, very peaked. And so that's odd because the combination of these two random vectors is not resulting in normally distributed x and y coordinates. So what that means is this shot target is no longer a bivariate normal distribution. As a matter of fact, if we go over to this 3D histogram, again, it's all built with formulas, and so we can look at that, and you can see once it updates here, look at how peaked it is in the middle. And again, this is just odd. Now, one nice thing about Excel is I can come over here, do a 3D rotation, and we can move around and kind of look at different angles this thing. And you can see it does look to be sort of a cone shape, but it's very, very peaked in the middle. And so again, this is one oddity of the exact way he's doing his simulation, is that it does not appear that his random vectors end up with a bivariate normal distribution on target, which is the standard assumption in ballistics. So if I go back to my original data, I'll just show you a few more things that I have on this sheet. I will be uploading this Excel file so you can play around with it if you want. I don't mind sharing this. I just did a couple of tests. The mean dispersion ends up being a little under 0.4 inches. And again, this is what I would call a 1 MOA rifle. But the group size, the way we measure it, is a maximum dispersion rather than dispersion around a center. And so here the average around center is basically, you can think of this as like the mean radius or something of a group is about 0.37, 0.38. The maximum deviation over 100,000 shots with this 1 MOA rifle was 1.52. So the largest error was only 1.5 inches in the simulation. Also, circular error probable is a number that you might come across in ballistics. So there's a formula for that I've got plugged in. And if you have your x and y variables both using the same standard deviation, and mine are both 0.3 standard deviation, this equation tells you the distance around center that will catch 50% of the outcomes. And so the CEP calculation says that, 0.354 inches, that circle would catch half of the shots. And my simulation result, so what I do is I just find the median value, and that would catch 50% of the shots, is pretty much bang on. So my simulation matches ballistic calculations pretty well. Let me show you what happens if you drop in this randomly generated vector data that he seems to be using in that Blackburn defense video. And I plop those in as values, let everything update. Now I come down here and you'll see that the circular error probable, now the calculation is off compared to the simulation because the distributional assumptions are now violated because circular error probable is based on a bivariate normal distribution. And so you can see that this generates an error of 4.5% compared to my baseline, which was almost exactly correct. And so that was one last thing that I noticed when playing around with his simulator is I think the way he's simulating his data is putting some weirdness in there. Now, one interesting thing is it doesn't really change the way the deviations work. So again, I don't want to nitpick too much. Many of the conclusions that he draws in that video are absolutely correct. Your deviations are not going to look normally distributed. But anyway, I don't want to harp on it too much because I'm not being overly critical. I think it's a really interesting video that draws some really interesting conclusions. I don't know if I buy his empirical results because, again, the expectation that you won't see anything in the middle of a target is, to me, just incorrect. You should see the bulk of your shots landing in the middle because that is the highest probability density. Now, that doesn't mean that all your shots are going to hit bullseyes. Again, you can calculate this stuff. It's, not crazy math to do this. And, on this kind of topic, one thing that is interesting to point out is the bigger diameter your bullet, the more likely it is that you get a bullseye. So if I scroll down and I've reverted back to my data with the normally distributed X and Ys, if you move to like a 308, so if you use a larger bullet, the probability of getting a bullseye goes up because your error doesn't really change, but the projectile size does. And I mean, you can think, like, if you're shooting a cannon at something with an 8-inch diameter ball, you can hit the center relatively easy because all you got to do is get your point of impact within 4 inches of the center. So you really, you can have a 4 MOA rifle and hit the bullseye rather easily if the diameter of your projectile is huge. And so, like, if you get up to like a 45 caliber projectile, all of a sudden, if you've got a 1 MOA 45 caliber rifle, you should be getting bullseyes like 25% of the time, compared to if you're using like a BB gun with a .177 caliber, only 4% of the time should you be hitting bullseyes. So it's rather funny how bullet diameter impacts the probability of hitting bullseyes, even given a rifle of equivalent accuracy. The bigger your projectile is, the more likely it is that you actually have a projectile strike the center of the target. So if you're shooting a 223, and I guess, you could get really precise and say a .224 caliber bullet, about 6.6% of the time with a 1 MOA rifle, you'd be hitting bullseyes. With a .264, you push that up to 9%. If you go up to a 284, so a 7 millimeter, almost 11%. So the bigger the diameter of your projectile, the more likely it is that you get bullseyes. There you go. There's a good way to cheat as far as hitting 10 rings on your targets. But anyway, I think I've probably gone into this in depth enough. I will upload this sheet so that you can play around with it. And if anybody sees any errors I made, please let me know. I think I did everything correctly based on standard ballistic assumptions. I mean, the one caveat is that, the standard ballistic assumptions that X and Y are both equal in standard deviation, probably a little flawed. It's probably a little bit of an ellipse group instead of a circle, but that's well beyond what we really need to worry about. But, technically I'm using a laser beam in this model, but it's good enough. Pretty close. And again, these are the same calculations that you'll see in a lot of military ballistic stuff. Okay, well, that's it for the video. Again, as always, if you've got comments or feedback, feel free to leave it down below, and feel free to play around with this sheet and let me know if you see any errors.